হুম। কোথায়? হ্যাঁ ঠিক আছে, ঠিক আছে, ঠিক আছে, ঠিক আছে। হুম। Okay. So these are the definitions. So the communality, the definition is given. Eigenvalue, the eigenvalue represents the total variance explained by each factor. Factor loadings are simple correlations between the variables and the factors. Factor loading plot, a factor loading plot is a plot of the original variables using the factor loadings as coordinates. A factor matrix contains the factor loadings of all the variables on all the factors. Okay. So now there are also some assumptions, okay, of confirmatory factor analysis. Like for example, no outliers in the data set. I have discussed about what are the outliers. Okay, while I have discussed on the box plots. Okay, normality of the data set. I have uh, already said that how to see, how to check the normality, the adequate sample size. Okay, that you also need to check. And data should be metric in nature. It means on interval and ratio scale. Usually it is performed in based on Likert scale. Models are usually based on linear relationship between the variables. Multicollinearity is necessary because variables must be highly associated with some of the variables, so they will load into the factors, but all of the variables should not be highly correlated except when only one factor will be uh, present. Okay, it is best for analysis to have group of variables highly associated with each other and not correlated at all with other group of variables. Then there is departure from normality. Homoscedasticity and linearity can apply to extent that they diminish observed correlation. It means as long as the correlation among the variables is not vanished, because this correlation may help in grouping. So what I would like to say that these assumptions, actually you don't need to concern, you don't need to check at all these assumptions. Okay, because in order to perform confirmatory factor analysis or structural equation model, when you will be going, there are some certain tests that you need to perform earlier, and based on that test you can automatically you will be validating most of these assumptions. Okay, so you don't need to separately check all those things. There should be, whenever in order to perform, whenever you will perform some confirmatory factor analysis model, suppose you will or whenever you sorry an exploratory factor analysis model, you will be having, suppose a lot of data, a lot of variables you will have. Okay, so those variables will must be very highly correlated with each other. Okay, but all of the variables should not be correlated unless there are only one factor. Okay, why? Because unless there is correlation, then how can you group them? Those group, they will be only if some variables are very highly correlated, then only they can form a particular factor, okay, or a particular constant. So that's why the multicollinearity is essential. So we can check those things. There are certain tests that we can check. Okay, so let's have a look at an example that will be better. Okay, suppose uh, the example that we can take, uh, suppose here we have yes, so in this example we will use two examples. Okay, So in this example, we examine students' assessment of academic courses. We restrict attention to 12 variables. Okay. So you have got 12 variables. Those 12 variables you have mentioned column wise, and row wise you have taken the data from the students. Okay. And you are using a score on a 5-point Likert scale. That means the scores can be either 1, 2, 3, 4, and 5. And they will represent the degree of the severity of the score or severeness that will be represented by the degree of the Likert scale. Okay. So this is the snapshot from SPSS. Okay. This is the snapshot from SPSS. This is and this is you are using. Okay. So now in this example, these are the 12 variables that you have taken: instructor, well prepared instructor, scholarly grasp, instructor confidence. So like these variables you have taken. Okay. Now another take a look at another example. This is actually this example has taken from the Lawley and Maxwell. Okay, this is the interface. Okay, so here the general intelligence of 220 students are actually studied. So similar along the row wise, you are proposing, you are taking the scores of the students, and these are the variables: Gaelic language, English language, history, arithmetic, algebra, geometry. So these are the variables. Okay, and you are getting the scores from 1 to 5-point scale or maybe something else, and you are getting your the feedback matrix that you are having. Okay. Now, how you need to confirm the factor analysis? What are the steps? What are the broad steps or the basic steps? The basic steps are: the first step is the correlation matrix for all variables is computed. The second step is factor extraction. Third step is factor rotation. And the fourth step is make final decisions about the number of underlying factors. This is basically nothing but your conclusion. Okay. So first step is the correlation matrix. Okay. So just have a look at this correlation matrix that the earlier example that we have taken: x1, x2, x3, x4, x5. This is the correlation matrix. Okay. So you can see that in this correlation matrix, lot of values are there which is greater than 0.3, 0.33, 0.32, 0.35, 0.33, 0.67, 47, 46. Lot of values are there which are beyond 0.3, which are greater than 0.3. It means it indicates that 0.3 over 0.3, it is noticed that they have got a very high correlation. If correlation coefficient is greater than 0.3, it means that this is a very high correlation. Okay, this is the value of the R. I have already described what is R, okay, or the correlation coefficient. So these are the values of your R or correlation coefficient. Okay, so you can understand that in your data set, the variables that you have taken, there is a lot of those variables. It is possible that those variables can be grouped because there is very high correlation in many of them. Okay. So now we will perform two tests simultaneously. These are very important actually, because these are actually telling you or saying you that your data is appropriate for it to perform the confirmatory, to perform the factor analysis, be it confirmatory factor analysis or exploratory factor analysis, whatever it is. So this is one is Bartlett's test of sphericity, and another is Kaiser-Meyer-Olkin measure of sampling adequacy or KMO test. Okay. So what is Bartlett's test of sphericity? It tests the null hypothesis that all the correlation between the variables is zero. It also tests whether the correlation matrix is an identity matrix or not. If it is an identity matrix, then factor analysis becomes inappropriate. Okay. So it is basically checking that whether this is the Bartlett's test of sphericity. It is checking that whether uh, the correlation matrix is an identity matrix or not. Okay. So your null hypothesis is that it is actually not an so whether it is an what is actually identity matrix, first let me tell you. So in identity matrix, all the diagonal elements, it will be 1, but all the off diagonal elements, these elements will be 0. Okay. What does it mean? It means that one particular variable, it is only related to this itself, but it is not correlated with some other variables. Okay. So that is actually known as the identity matrix. So if it is an identity matrix, then the structural model, the confirmatory factor model, it is not appropriate. Okay. So it is testing that, because in order to make sure that there is sufficient correlation among the variables. So basically Bartlett's test of sphericity is a measure to identify that whether your matrix, it is sufficiently correlated. That means whether the variables that you have taken, that is sufficiently correlated or not. It is a measure of that. And KMO, this is a measure of the sample adequacy, whether the samples that you have collected, whether it is sufficient or not. Okay. Okay. And, if you have values greater than 0.5, it is written, but it is actually, strictly speaking, it should be greater than 0.6 actually, 0.6 or 0.7. If it is like that, then you can see that you can say that you have enough sample size. Okay. So have a look at this thing, the KMO and Bartlett's test of sphericity. Okay. So you can see here that the significance level is under 0.05. So there is sufficient correlation, and the KMO value is 0.934, which is very close to 1. So as it will be more close to 1, that means the sampling is adequate. Okay. So that means you can apply your confirmatory factor analysis model. As a rule of or factor analysis model, as a rule of thumb, you need to have 300 cases, or 200 to 300 the samples you need to have in order to conduct the factor analysis, or say or structural model. Even you need to have at least 200 to 300 sample size, and number of observations are greater than 20 cases per variable. 20 variables ideally have been greater than 400 cases. Okay, so that means the 20 cases will be there for per variable. So it also depends upon the variables, but I have seen that the researchers, they are suggesting that whatever be the number of variables, but at least 200 to 300 sample size, it is ideal for to conduct I would say structural model, because you would actually perform structural model. Okay. So the next step is factor extraction. Okay. So this, what I was saying, the primary, in this case of factor extraction, when you will be performing this step, second step of factor extraction, you can use principal component analysis and it is, in fact, it is most commonly used extraction method. But reviewers nowadays, they are giving objection on this method, principal component analysis method of factor extraction. Okay, so I would say, but if you use principal axis factoring method, it is high possibility that no reviewer will give you the objection. Okay, why? Because this is based on the common variance or the shared variance, but this is based on the total variance. Okay, when you will be extracting the factors, this will be based on the total variance, not based on the common variance. Okay, so that's why this factor extraction you use, I would say that you better you use the method of principal axis factoring. Okay, so you will be getting these kinds of table you will get. Okay, so initially the number of variables, suppose if you have 23 variables, you will have 23. They have used the extraction method of principal component analysis, but whatever method you use, you will get the same number of the factors it will be extracted. Okay, that means each variable will I mean the 100% of variance will be represented by the factor. Okay, so now after that, after the extraction, before extraction, you can see here that suppose Q01 is 1, initial extraction is 0.435. What does it mean? It means 43.5% of variance in Q1 is common or shared variance. Okay, by all these 23 factors. Okay, that is the shared variance or common variance. Before extraction, there are as many factors as there are variables. N is equal to 23, so that all variance is explained by the factors, and communality will be 1 because there is no data reduction during that time. And after extraction, some of the factors are retained, others are dismissed. Others are dismissed means in which case it is, if it is 0.3, these are dismissed. This leads to a welcome data reduction. Now the amount of variation in each variable is explained by the factors in the communality. Okay, so let's take a look at this slide. Okay, so here you can see that what is happening. Okay, so the evaluation of 2 cooking methods for fish. So this is actually known as the factor matrix. This matrix is known as the factor matrix. Okay, there you can see that 4 variables are, you had 4 variables. Okay, and you have extracted 2 factors. Okay, you have extracted 2 factors, and here this is the example for communality, and this is the example of the variance, or these are actually known as the eigenvalues. Okay, so if you square it, these factors, okay, suppose 0.77 square plus 0.45 square, you will be getting this communality value 0.803. This value you will be getting. Similarly, if you square and then if you sum it, or sum all those values, 0.77 square plus 0.67 square plus 0.8 square plus 0.79 square, so you will be getting 2.34, these values. Similarly, in this way, these values you will be getting. Okay, so now the how many factors you will have to extract? The rule of thumb is that all included factors prior to rotation, the rotation phenomena I will discuss later, must explain at least as much variance as an average variable. Okay, at least as much variance as an average variable that the factor must actually extract. Basically it will depend upon the nature of the eigenvalue. Okay, that I am coming to the part later. Okay, first let's talk about the communality. So the communality here in all the cases, you can see that the communality is greater than 0.5. Actually, the greater than 0.5, that communality is actually preferred. Okay. So x1 is this variable has a communality of 0.80370, like this, 80%. So proportion of each variable's variance or shared variance that can be explained by all the factors. Okay, this is actually known as the communality. That means x1, the variance of the x1 variable, okay, there is 100% variance of the x1 variable. So out of this 100%, or the total of 100%, 80% of the variance of x1 variable can be explained by factor f1 and f2, or if there are more factors, or of all the factors. This is the meaning of this communality. Suppose 0.84, that means 84% of the variable of x2, 84% of the variance of the variable x2, that can be explained by factor f1 and f2. Now you will ask that where are the other variants? The other variances are the uncommon variance. They may be the unique variance for the variable x1 or x2 or x3 or x4, or there are some error variance. Okay. So these are actually known as the communality. Okay. Now, if you think about the eigenvalues, if you talk about what is the eigenvalue means total variance that is explained by that particular factor to express the variables, to express all the variables. For example, suppose 2.344, this is the eigenvalue. Okay, and the proportion is 0.5862. Okay, so what does it mean? It means that 58% of the the variance of all the variables, okay, taking into account all the variables, that is actually explained by f1. F1 explains 58% variance of the variable, taking all the variables all together. Okay, so this is the meaning of this eigenvector. Okay, this is the value of this meaning of this eigenvector. Eigenvalue. So now the thing is that what you will be seeing that there is a lot of factors that have been extracted after performing this kind of principal axis factor. Now, which particular factors you need to choose? Usually, the values that are greater than 1, those factors are actually retained. But in some cases, it is known as Kaiser-Gottman criteria. If the eigenvalue is greater than 0.7 or greater than 0.7, those values are also retained. Okay, you just have a look at this one. Here you can see that suppose you can see that 3.046, 1.801, 1.009, 0.934, 0.840, 0.711, all the different, you can see that these are the eigenvalues, and 10 factors have been extracted. Okay, so out of those 10 factors, only the 3 factors have been retained. Those have greater than 1 value. And sometimes some researchers also prefer that above 0.7 values they will be considering. So in that case, you will be retaining 6 factors. Okay, it basically depends upon your ease. Okay, what or comfortability. Okay, whatever you will, if you find that I am capable to handle 6 factors very easily, then you can obviously you can retain the 6 factors. There is no problem. Okay, so it will depend upon the researcher, what the researcher actually prefers. Okay, but again, the main objective is to reduce the data and to interpret something meaningful. Okay, and you will be plotting this is known as the scree plot, and you need to find out the elbow. Okay, how the scree plot is drawn? You can see that along x-axis the number of factors that are being represented, and along y-axis the eigenvalues are being represented. Okay, along y-axis the eigenvalues are being represented. So uh, for each factor you are basically plotting all the eigenvalues. Okay, and you can see here that 1, 2, 3, in these cases the eigenvalues are greater than 1, or the very much close to 1, but after that uh, the values are again it is very less values. So that's why the elbow will be this is actually the elbow, you can see, and up to elbow those values you will be considering. Okay, 1, 2, 3, these values you will be considering. And even if you do not draw this curve scree plot, then also there is no problem, because from this table itself you can understand that which values are greater than 1. This is the just this graphical plot is there. This graph is nothing but the plot or the figure for this table. Okay, this is nothing but the figure or the plot for this table. Okay, this is, so those values you will be only considering. Okay, so after that you will have to choose that which particular variable is loaded onto which particular component. Okay, that you need to choose. So those things I will discuss later. Okay, in the next class I will discuss which particular factor should be loaded onto which particular variable should be loaded onto which particular factor, how to do that, and what is the factor rotation. So that I will tell you. Okay, now I am going to stop.